Thank you for joining us. My name is Laura Roberts, and I'm the AVA Marketing Manager at PDS Group. For those of you who may not be familiar with PDS AVA, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. Today's session is presented by Matt Boyer, a senior geologist in PDS's AVA team, who is currently supporting the development of AVA saturation. Geoscientists don't often have the luxury of calculating multiple saturation height functions, but doing so can have important implications for the investigating volumetric uncertainty. Over the next half hour or so, Matt will introduce several well-known methods for deriving saturation height functions, including the Leverett J, the Skelt-Harrison, and the Cuddy FOIL. He'll also show other general methods for calculating and modeling saturations in reservoir models, and highlight the differences between the classical methods and more general approaches. The methods will be demonstrated using data from two fields. The wells have suites of electric logs with both routine and special core analysis data available. We'll kick today's session off with a little housekeeping and then just jump straight into Matt's presentation. If you wish to ask questions throughout the seminar, please type them in the question box in your GoToWebinar panel at any point during the presentation. We've allocated some time at the end of the webinar for questions and answers, and we'll go through your questions at that time. Alternatively, if your question requires a little more explanation, you can also use the raise your hand function, and I'll turn your microphone on so that you can ask the question verbally instead. We're also very keen to hear your thoughts on saturation height function workflows. So we'll be running a couple of polls throughout the session to gather your views and kickstart a discussion. Matt joined PDS Group in 2017 to lead the team who brings you over saturation. Matt has over 10 years experience working in the oil and gas industry. In that time, he has worked for Shell in the Netherlands and for Helix RSD and Fairfield Energy in London as a development geologist. More recently, Matt worked as a reservoir modeler for Merlin Energy. He has worked on the exploration and development of a range of assets across the globe, with a particular focus on the Ukraine, Nigeria, Niger, and the UK North Sea. Matt holds a BSc in Geology from the Royal School of Mines at Imperial College London and an MSc in Structural Geology and Geophysics from the University of Leeds. Without further ado, please let me hand over the time to Matt.
Okay, so hello, good morning, everybody. Or good afternoon if you're still in the UK. Thank you for the introduction, Laura. That was fantastic. Okay, so what am I going to be talking to you about today? Well, basically saturation height functions in the context of reservoir models. So what I've done is I've split this talk into two parts. So the first part we're going to have a look at some saturation height functions. And a bit of an introduction to saturation height functions. Then we'll have a look at the functions in action. So we'll see a couple of case studies. And then in part two, I'll introduce a new software product which is designed to support the saturation modeling workflow in the reservoir modeling domain. With the aim of the application basically is to try and make that conversation between geologists, reservoir engineers, petrophysicists a little bit easier and create a sort of a shared space for saturation modeling. Okay, so I just jump on to the next slide. He says if he presses down arrow, there we go, it works. So one of the major deliverables of petrophysics is, in addition to the saturation logs, porosity logs, and rock typing, and a lot of the very good work that the petrophysicists do, is the saturation height function. Now, armed with a height function, geologists, reservoir engineers, petrophysicists, we can predict saturation anywhere in a reservoir for a given height above the free water level and for a given porosity permeability. So broadly speaking, there's two approaches for calculating these height functions. So we can take them from core data. So these are directly measured and quite reliable models from the capillary pressure curves, directly measured in the lab. But unfortunately, the measurement scale and conditions are vastly different from those that we see in the reservoirs. So some uncertainty does then obviously creep into the calculations. At the log scale, that's got the advantage of being at reservoir conditions. But again, variations in things like AM, NRW, the electrical parameters, or perhaps even thin bed effects that affect the resistivity response all have an impact on the accuracy. So ideally, what we want to do is to use all of the available data, investigate differing approaches, and try and decide which function is best for our data, which is best for our reservoir, and try out different approaches. And unsurprisingly, there's several different methods have been proposed over the years. So we've got those of Leverett and Johnson, or say the more log-based approaches of Steve Cuddy's FOIL function. The Skelt-Harrison approach is obviously is both log and PC data based as well. So as Laura mentioned at the start, what we're going to do is have a couple of polls throughout the webinar. So we'll start with the first one, and the first poll is basically, the question is, what tools do you use at the moment to construct saturation height functions?
You can now go ahead and select the option which is appropriate by clicking on your screen. Great, thank you all for voting. I'll close the poll now, and you'll be able to see the results on your screen in just a minute. The majority of you voted that you use Petrel to calculate your saturation height functions. And then it was an equal split between Microsoft Excel, specialist petrophysical software, and other tools such as old-fashioned pen and paper. I should also add that someone commented that they use an accessory module within Petrel that is built by Segal as well. So thank you for your answers.
Yeah, that's wonderful. Thank you for your answers, and thank you for sharing that you use the Segal module as well. That's very kind of you to share that information. So it's good to see that we've all got a reasonably broad experience of saturation modeling in various domains. So hopefully there'll be something of interest in this first part, where we have a look at different functions in case studies, and then when we have a bit of a look at the AVA saturation application in a few moments. So as I've mentioned, I've put together a couple of case studies. So this is just an introduction to the different methods that we used in the case study. So I had capillary pressure data available, so it makes sense to start with the Leverett J function and use that one. I quite like Steve Cuddy's FOIL function. I like the simplicity of being able to implement that. So I use that only using log data. Then use the Skelt-Harrison function as well, and also lastly, I tried a couple of Excel's very own regressions, such as the log and exponential regressions. So basically, the question I'm trying to answer is sort of which method is best, or does it matter which one we use, or actually is it as simple as that? So let's crack on. On to the next slide. So the first case study comes from Northwest Australia, from the Crooks field. It's located in the Browse Basin. The field was discovered by a company called Nexus Energy in 2000. Discovery well Crooks 1 encountered fluvial reservoir section called the Noma Formation. Usual suite of logs was acquired in the well, so we've got the gamma ray density, neutron resistivity, and so forth. And we've also got some core data available, a limited amount of core data, which you can see by the red points on the right hand side, or if you can see where my mouse is moving at the moment, the core data is just there within the sort of the upper Noma sand. So not a huge amount of core, but at least it's something to start with. So we had core porosity, permeability, cap curves, and so on. The well was tested from two intervals, one in the shallower formation, one in the slightly deeper formation. Rates in excess of 30 million scuffs a day, so that's pretty good. And the pressure data that was obtained in this well gives us a pretty good handle on the depth of the free water level. So that's also a big help in actually being able to start to try and piece things together. So we'll skip over Crooks 2. Crooks 2 was drilled off structure to the northeast. There was a sidetrack which discovered gas in the shallower Montara formation, which is also the case for wells Crooks 3 and Crooks 4. So on the very right hand side here, again, if you can see where my mouse is moving, we have the log suite from Crooks 3. And we can see the gas in the Montara sand at the top, and then also below that we can see the gas in the Noma Ray formation there. So the challenge from this data set that we've got here is to start to derive some saturation height functions and see what we can learn from it, and see what we can figure out from this. So as I mentioned, Crooks 1 had capillary pressure data available, so it made sense to start at that point. So the logs on the left-hand side, again, this is the same depth interval as we saw on the previous slide, where the capillary pressure data it was taken from. So we've got the PC, the SW curves displayed in the center of the screen, but the porosity range here is not ranging a huge amount. It's about 15 to about 21%. So that's not entirely representative of the porosity distribution that we see within this well itself. And indeed, if we then jump on to having a look at the J versus SW plot, so this is just on the right-hand side, color coded by the different samples there. There isn't a huge amount of spread across that data point, so across that data. So rather than using restrictive porosity bandings over quite a small range, I did actually cheat a little bit, shall we say, and just derive the global J function from that data to then be able to apply that function to my reservoir model. So what we have plotted up here is the Archie log derived saturation. So I'm just trying to compare the Archie saturations back to the J function just to get a feel for the fit of that curve. So what I'm seeing here is in the shallow sands at about 200 meters above the free water level, we're getting quite a good fit to the data. And then as we get closer to the free water level, it's doing a reasonable job between about sort of 20 and 100 meters. Getting really close down to the free water level there, we're starting to see maybe that fit isn't particularly great. Maybe we need to apply a bit of a shift to that curve. But all I'm doing in this case study is just testing different height function examples and just trying to see what the differences are between the different approaches. So I haven't actually applied any tweaks or anything like that to that particular curve. So let's jump on. So the next couple of methods. So the Cuddy FOIL function was the next approach. So what we've got here, two plots. So I ran the FOIL function twice. So on the left-hand side here, we have the FOIL function, and this is just using the default regressions that you get from Excel. So I plotted up bulk volume of water versus my height above free water level. On log axes, I got my power law regression, and I was able to use the A and B constants from that regression to derive this FOIL function. You see it's doing a reasonable fit. It's perhaps a slightly better fit closer to the free water level, maybe not so much at around 50 meters above the free water level, but it's still a pretty good fit to date. So I was quite happy with myself. I was quite pleased. I've got my FOIL function working. So the next stage was to then do that regression analysis myself, so perform the least squares regression myself, so that what I can do then is I can begin to tweak the A and the B constants to actually try and change the fit of that FOIL function through the data. So that's exactly what we're seeing on the right hand side here with this second FOIL function plot, is a slightly altered fit just by moving the A and B constants from the power regression. So what we can see is that we're getting a bit of an improved fit at around about below 100 meters to the free water level. As we get a little bit further away, we're getting a bit sort of it's not matching the data as well. I've not actually clipped this to or fixed it to a reducible here. This is just a case of just testing different examples. So the next two functions that I then used were next function that I used twice was the Skelt-Harrison approach. So this provides quite a bit of flexibility to fitting height functions to the data. So again, much the same process as for the FOIL function. It's just to run two different ways of fitting the curve to the data point. So the difference between each of the curves is just it's just purely a fit of the A, B, C, and D constants that you get in the Skelt-Harrison function. You can see that on the right hand side in what's termed version 2 here, they've applied a little bit more of a bulk shift to that curve just to try and fit some of this data, which is at around about sort of 15-20 meters above the free water level. It's doing an all right job, but it's just a case of testing this the different examples and seeing what impacts they have. So if I jump on to next slide. So the next stage was, okay, well, I've tried some of the classical methods and actually got some functions out of the data, and I've actually managed to get somewhere. So what else can we do to try and predict saturations within the reservoir? Is there something else I can begin to look at? So I figured, well, I've done a bit of work in Excel. What I can see is that you've got different regression methods available. So just by plotting the water saturation against height above free water level, or bulk volume of water against height above free water level, you can begin then to start sticking different regressions through the data sets. So what I have on the right hand side in the three blue lines that you see on that chart there, the first one that's sort of down at the bottom there is the exponential regression, and the very light blue, that's my logarithmic regression, and then the very wibbly wobbly wavy line, just because I could, was a sixth order polynomial. Now that doesn't play any further part in this analysis. That's just showing that you can just basically stick a curve through any set of points and try and get an answer out of it. The line down at the bottom, which hopefully if you can see where my cursor is tracking, is the first exponential method. Now that doesn't necessarily look too clever. That gets to about 25% SW at the free water level. So what the red line is, that's the second exponential, what I've termed the fixed exponential, where I've fixed that y-intercept at about 70% SW there, just to try and force the fit of that curve through the data just perhaps a little bit better. And obviously it's missing some of the points between about sort of 20 and 80 meters above the free water level, but it's just trying to get away from the 25% SW at the free water level, which doesn't necessarily look too great. So what was the point of all this? Because I've sat there and done a bit of work in Excel, and I've created some height functions using classical methods, using Excel methods, and I didn't do it just because I was bored. I was trying to actually find some conclusions. So the data that we had from the Crux field was quite extensive, and we were able to do a bit of seismic interpretation and pixel faults and all that sort of good stuff. So I was able to build a reservoir model from Crux. So the model I built was a sector model focusing on the Crux 1 and Crux 3 wells that you can see outlined in red here. Example of the reservoir model on the right hand side for those geologists who are dialing in. And the idea is that now that I've got my reservoir model built, I can model my facies in the usual sorts of way, I can model my porosity in the usual way, and so forth. And what I can then do is use this massive, great big long if statement of all the different saturation height functions that I've developed, and apply those to the reservoir model. So I'm having to be careful, of course, of getting the syntax correct between Petrel and Excel, and doing all the various different clippings and setting things to 0 that you need to do to get things to work properly in Petrel. So what does all this actually mean? All right, well, there's two ways in which we can QC what we've done. So the title of the slide is instantly wrong. So the first QC step is just to have a look at the predicted saturations versus the log-based saturations. So what we've got here is this just for well Crux 1. So the different methods shown along the top. So the FOIL function, Leverett J, the Skelt-Harrison function. Got my exponential and my log based regressions from Excel. The exponential fixed is the third one in from the right there, and then the version 2s of the FOIL and Skelt functions that are at. So in red is the Archie log derived saturations, and in black is the predicted saturation height function saturations. So we're seeing pretty much all of the methods, with the exception of that fixed exponential one there, that they're all doing a pretty good job of matching those saturations in the shallow and no moraine stand, which is probably unsurprising. We're getting close, or if not at irreducible saturation at that level. As we move down through the section into the NOMA B, where we start to get into the transition zone, this is where we start to see more of a divergence. So you can see most of the methods there are actually are a little way off the Archie saturation. So if we have a look at the FOIL function and Leverett J on the left hand side here, both of those are over predicting the hydrocarbon quite a bit. The fixed exponential as well, that's way off. But actually probably the best fit that we've got there is that FOIL function version 2, where I've in particular through the lower part of the transition zone, where I've actually managed to force the fit of that curve. So I'm actually beginning to build up a bit of a picture as to which method do I want to use. Do I want to use a combination of different methods, and just the impact that these different height functions have when I'm trying to represent my saturations in the reservoir. The next stage then is to take a look and say, okay, well, what's the difference in terms of the gas in place that I can calculate? So this is just for the for the sector model that I built. So I have a reference case volume in the green bar there. Now that's not entirely representative. That's just using a constant fixed saturation all the way down the wellbore, but it gives a bit of a ballpark estimate as to what sort of JIP number we'd be expecting. So actually, between all of the different methods, ignoring that fixed exponential, we get about a 12% difference in gas in place. If we start including that outlier, that fixed exponential, we actually increase the difference in the gas in place there to about 31%. So I guess the key takeaway there is that the variation in gas in place that we can calculate from these different methods, it's actually worth investigating which method that we want to use, or do we in fact actually want to use a different combination of methods depending on where we are in the reservoir. And that obviously also translates forward to slightly more complicated situations. For example, if we've got multiple fault blocks and multiple different free water levels, does one method work well in one area versus in another area, and so on. We can start to actually look at the data and figure out which methods are best for us, and actually start to investigate these multiple scenarios and multiple different sources of uncertainty. Okay, so that's a crux field. So we're staying in roughly the same part of the world. So the second case study comes from onshore New Zealand. So this is the Kapuni field. It was discovered in the late 1950s. 23 wells drilled into Kapuni over the years, with production beginning in about 1969. So it's been around for a while. We managed to get some data from Kapuni. So we've got wireline logs for about 18 of the wells. A couple of the wells had capillary pressure data available in them, which was a good starting point again. But Kapuni is actually quite a good example of being petrophysically pretty challenging and pretty tricky. So what we can see on the right hand side is the caliper log in the sort of the dashed burgundy or red or whatever colour you want to call it, which is showing a fair amount of borehole washout pretty much all the way down the reservoir section there. And obviously you can see the effect on the density tool as well. So that makes it quite tricky to be doing some petrophysics on that, and in particular for myself from a geological background, doing the porosity calculations and stuff, I need to take a bit of time and actually think quite carefully. There's also thin bed effects as well, so we do have averaging of the resistivity response. So again, there's quite a bit of care that needs to be taken in terms of actually doing some porosity and SW calculations from the logs that are available. So you can probably imagine I was quite pleased that there was the capillary pressure curves available. Unfortunately, one of the wells, Kapuni Deep 1, which had the capillary pressure data, that was, well, the clue was in the name, that the core interval in that well was about 4,000 feet below the reservoir, so not exactly representative of reservoir conditions. So if we have a look at some PC data that is representative of reservoir conditions, so this is the Kapuni 12 well. So we can see in the northern part of the field here, just highlighted in the black box. So yeah, about 20 meters of core from the well. About 10 samples were taken, which had PC measurements. Unhelpfully, what I've not done is put the legend on this particular chart, but this is color coded by porosity. So we see there's quite a bit of spread across the porosity range there. So what I've managed to do is then break that data out into different porosity bands. So I've got six different porosity bands from that data. I can derive a J function for each of those bands, and then I can apply those height functions to the reservoir model. So the idea behind this was to have a look at see again what impact different methods have on the reservoir model. There wasn't a huge amount of point in just applying the data from one J function and calculating volume. I've got nothing to compare and contrast with. So after a bit of head scratching, a bit of tricky calculations, shall we say, I managed to derive some pretty basic petrophysics. So from that, I was able to plot SW against height and get a Skelt-Harrison function that we can see on the right hand side. So now I've got a J function, I've got a Skelt-Harrison function that I can then start to try and compare and contrast and see what happens in my reservoir model. So the interesting bit about Kapuni is the fact that it's quite a broad, low relief anticlinal structure. So In the coastal regions where we're close to the irreducible saturations, we'd expect probably little difference between whatever method that we're going to use. But if we look at the area versus height above free water level plot down here, we can see that quite a lot of the volume of Kapuni sits close to the free water level. So it's quite important to actually do a bit of QC work and actually check the impact that your saturation model is having on the volumes that you're calculating, and also the match either back to the logs or matching to DStark, or however you're QCing your different method. It's important to test different approaches and consider those multiple scenarios. So what we can see in Kapuni is the fact that when we look at the transition zone volumes only, there's about 324 versus 299 Bs in place. So that's about an 8% difference between the two methods. That's obviously accounting for, it could be slightly more, it could be slightly less, depending on your view of the petrophysics that I've done for the calculating the logs there. So again, the idea is just looking at these different methods and testing various uncertainties that may come with these different approaches. So why was that of interest? Why have I just bored you all silly in the last few minutes and told you something that you probably already know a reasonable amount about? So obviously the uncertainty and saturation height functions does have an effect on the volume calculated. It has an effect on the way that you represent the transition zone within the reservoir model. So we should be considering different methods. We should be considering multiple scenarios. It's obviously not the only source of uncertainty in reservoir models. We have things like the depth conversion, gross rock volume, porosity. Perhaps, you know, if you start tweaking AM and N or start tweaking RW, that's obviously going to have an impact on your Archie log. That'll have an impact on your height function. So there are other sources of uncertainty, but nonetheless, we should be taking a look at what's happening with our saturation height function. So the reason for putting all this all together is to try and highlight some of what we're doing here in PDS. And what we're doing in PDS is trying to support specific aspects of the reservoir modeling workflow. So we can remove some of the labor-intensive manual tasks. We can make your job a little bit easier. So you can focus on the job at hand of considering those different scenarios, look at what your data is telling you, and actually start to consider different approaches to doing things. So to support the water saturation modeling workflow, we've developed a tool called AVA Saturation. So what the application is embedded within Petrel. So it's a cloud-hosted technology to support building saturation height functions and applying them to the reservoir models. Being cloud-hosted, that's quite cool, because what that means is that we can deploy new updates and new functionality really quickly. So if you're using this application and I don't have a particular, and we don't have a particular method that you like in there, so you want to see Brooks Corey within the application, then you can drop us an email, you can get on the phone and say you want to see a particular method. We can be very flexible and accommodate that very quickly, and because we're cloud hosted, we can deploy that update very quickly. We're trying to also make the building of these saturation height functions straightforward by removing different bits. Like, so if you're using Excel at the moment, the time-consuming elements such as data import and export, the manipulation of the data, if you're using Petrel, the regression analysis isn't necessarily the best within Petrel, so we can support this support saturation modeling by using industry standard approaches. The application is basically split into two parts. So what we have is this explore data area, where we're trying to provide you with a bit more flexibility and just make life that little bit easier for being able to plot things up and test different assumptions. So if we look on the right hand side here, I have two charts. I have the chart at the top, which has got the water saturation logs plotted against height above free water level, and then at the bottom I've got bulk volume of water versus height above free water level. So one of the assumptions that Steve Cuddy has in his FOIL function is that BVW is a function of height alone. So we can see the data is collapsing nicely onto a trend, which is just a function of height above the free water level. So perhaps in this instance, the FOIL function is one that is sensible and is applicable to use in the reservoir. If we then jump onto the second part, so we've got these things which are called saturation concepts, which you'll see in a moment when I jump into the application. So what these concepts do is they form the basis of the workflow. So they can guide you through the workflow. So if you're very experienced in this kind of work or you're inexperienced, it's not going to take you long to get to grips with what you need to do in the application. And before you know it, you'll be using it. It's not very time consuming to actually understand what's required of you. We do some of the calculations on the fly, so things like height above free water level, bulk volume of water, we do those calculations for you. So again, we've just removed that manual process so you can begin to test different functions. The industry standard methods that we're supporting at the moment are obviously the Cuddy FOIL function, Skelt-Harrison function, Leverett J as well. And this whole saturation concept document basically forms the basis of the audit trail. So all of the calculations you make, all of the decisions you make, any charts you produce, any height functions that you make, they're all saved and they're all stored within this this saturation concept document. So you've got this audit trail there. So when you, at the end of the year, when you go to your friendly reserves auditor, you can say, hand them a document and say, there you go, that's what we did. It's got all the input data in, it's got the function, it's got the bits of the reservoir model that you used, and you've got a very nice clear audit trail which they can sign off on and say, yep, we can understand what you've done in your saturation modeling there. Okay, so that's enough of PowerPoint for now. I think it is. Yeah, there we go. So let's jump into Petrel. So standard Petrel 3D window that I'm sure we've all seen at some point in our lives. On the left-hand side, we've got sort of a few grids that I've made of the crux field. So this is actually for the full field model and not the sector model that I had in the case studies. And we have so we can pick up all the different grids within the oversaturation application, and we identify all the contact sets that we have there as well. So if you enter your fluid contact into Petrel, which generally speaking you need to, you don't need to enter that again. We can just find that contact set and you can select the one that's most appropriate. And then it's the same thing for the input well data. So we pick up all the porosity, saturation, fascies logs, all the logs and all the wells that you're going to need to be able to start doing some analysis. So without further ado, I can either jump into saturation from the Windows pane, or we have the AVA tab just at the top. So let's just use that and just open the application. We're taken to our nice friendly, welcoming landing page. There's a few usual suspects in there, just to quick start guide to help you get started, user guide and so forth. But let's jump into explore data so you can actually take a look at what we've got. So first step is, because we're trying to keep that audit trail and that auditability, is to try and keep everything tied to the reservoir model. So you've put a lot of time and effort into building a reservoir model or a bunch of different reservoir models, and now you want to apply some height functions to that model. So select the grid that you're interested in, and this is then used for finding the contact set that you're going to use. And just click on full field contact. So we can now do the height above free water level calculations, should we want to, because we now know the depth of our free water level. So I just whack on some data in there and throw on the SW. So I've now got a nice little cross plot showing my porosity versus SW, the usual sorts of functionality you'd expect to just turn the zones on and off. And these are the zones which are being used for filtering that off from the reservoir model. If I want to turn on my fascies, I can now then change my Z-axis, and I'm now displaying things color coded by fascies. If I want to start having a look at different things, so I've got the height of a free water level plotted, so I can have a look at height of a free water level versus porosity, or even water saturation, for example. And the eagle-eyed of you will notice the BVW calculation that's done there. So again, we've got the plotting functionality to be able to get to grips with our data. We can create multiple charts and things, and we support the histogram charting as well. So that's just a porosity histogram. I can take a look at saturation as well. So once we've done that and we've actually begun to get to grips with the data and actually can identify any trends or test any assumptions, next stage then to create the concept, so we can start creating some height functions. So I can do that from this point and click create concept, and that will take me straight into a document. Or I can create one from the concepts list for you here. So this just gives you a list of all the saturation concepts that you have that you've created. So if you've been using this technology for a couple of years, you'll probably have a good few concepts. If you've only just started using, you might only have one or two. So let's open one that I prepared earlier. So the concept's now open. So as I said at the beginning, it's a guided workflow. So what you see on the left-hand side is this navigation pane. So it just guides you through all the steps that you need to do to create these height functions. The first stage is obviously to select the grid that you want to use and to select the contact set that you want to use. So you know which bits of the grid you want to use to filter in the data in terms of zones and segments. And we can also find the fluid contact, which is, or sorry, the free water level, which is most appropriate for that height above contact calculation. And then it's a case of scrolling through the application and basically putting the bits of the reservoir model together. So the first stage is to group the zones that you're interested in. So I've already done that here, but I can just quickly show that functionality. So I know that my my Noma sands contain the gas, so that's fine. I can group those together. Montara and Plover in Crooks 1 are both wet, so I'm not terribly bothered about those. Same with the reservoir segments. So Crooks 1 and 3, they're in communication, so I can group those two reservoir segments together, and it will use the data from those two segments to then be able to calculate the functions. And it's also the same process for the fascies. So select the fascies that you're interested in. So if you want to have multiple height functions for different fascies or different rock types, again, you can do that. You can accommodate that. If you've got 8 different fascies and you want to build one saturation height function per fascies, again, that's perfectly feasible. So we've done that, and we can put those bits together, and we can now start to begin to calculate some height functions. So one of the other uncertainties that you can begin to look at is the difference between what happens when you're modeling it at an upscaled level versus when you're using your wireline logs. So we can actually sort of take the upscale well logs and create a height function, and we can take the log interpretation and create a height function, and you can again start to play around, start to test those ideas and those multiple scenarios. So if I just turn on my upscale well logs, so I want to use the FOIL function, which I can select from the drop down method here. If I just select my upscale porosity and SW logs, and what this does is this then will give us the bulk volume of water calculation, and I can just enable those two data sources and click resulting function, and we have the BVW versus height cross plot that we can see there. If I want to use the Skelt-Harrison method, again, it's very similar approach. Just select the Skelt-Harrison approach, the logs that you want to use, and just click create function. If you're not very happy with the fit of that line there, I don't think that's a particularly great fit. What we can do is we can then just edit the constants and just begin to force the fit of that line through the data points. So all I've done is just change the A and the B constants there, and I've perhaps got a slightly better fit through that data. If I want to go back to the beginning again, obviously I can just hit restore to default. So let's go to the Skelt-Harrison, sorry, to the FOIL function. So what I've done already is I've actually already created a height function from the upscale data. So I'll just create one using the wireline data, and then we can take a look at the impact or the difference between those two functions. So just click resulting function again. I've got the FOIL cross plot. Same process as Skelt-Harrison. If we want to shift the line around, we can do just by editing the regression constants. And then once we've accepted these regression constants, that now means that we've got our saturation height function that you can see here highlighted in blue. That means that's now there, and it's now ready to apply to the model. The way that we do that is this function mapping workflow, and that just removes the need for those great big long if statements that you need. So imagine a situation where you've got 10 volt blocks, 10 different saturation functions, and they vary by fascies type, for example. You can use our function mapping, and all you need to do is just simply select the function you want to use, hit apply, and that will then apply this particular function to your reservoir model. So we hijack the Petrel geometrical modeling workflow. So as part of the generation of your 3D property, we'll generate the height above contact property for you. So I jump back into Petrel. So we generated the height above contact property as part of that process, and under properties in your reservoir model, we split out a folder which has got the title of this saturation concept that you've created, the timestamp at which you've run it. So I've just run that one now at 4:45, and the SW property then that you've just generated. So actually very quickly just remove the need for that if statement, and it's applied that function to the reservoir model. If I jump back into saturation, we have this history tab, which shows us the history of each of the particular functions that you've applied. So again, you've got that audit trail, and you've got all those data inputs and the final function then that you've used, and that's all stored within the application. So quickly you can see what's been done, and very quickly you can just repeat the process, so you know which bits of the modeling were used, and you know which logs and so forth, and you can very quickly just get back to that saturation height function. So it's not a spreadsheet, so it's just sat on somebody's computer somewhere where you don't really know what was done. So I hope that's given a flavour of the application. So just to quickly draw some conclusions from that demonstration, I'll just jump back into PowerPoint again. So what I did there was I just created a 3D saturation property using the log interpretation. I'd previously created a property using the upscale well logs, which we can see on the left on the left-hand side of the plot here, which is for the Crux 1 and Crux 3 wells. And when you run the volume calculation, and this is looking back at the sector model that I had, there's about a 5 BCF difference between those two scales there. So again, by making this nice and straightforward and a friendly interface, we can start to actually say, okay, well, is there a difference between my upscaled and wireline logs? Yes, there is, and you can quantify that difference and actually say, okay, well, which is the appropriate scale for stream modeling out, and then you can then go back and then QC this against your Dean Stark or your PC saturations and make sure that the fit of either your upscale function or wireline function is appropriate for the reservoir. Okay, so that's taken through the demo and through the couple of case studies. So we're going to have another poll now. So bearing in mind what you've just seen there, that we've got the FOIL functions, Skelt-Harrison, Leverett J available and so forth, what would you like to see next in our AVA saturation application?
As with the previous poll, just go ahead and select the option that is you think is most relevant. I'll be closing the poll in just a few seconds, so if you haven't already cast your vote, then please go ahead and do so. So not everyone voted in this poll, but of those who did vote in this poll, it's a 50-50 split between users wanting to see relative permeability calculations and a free water level prediction workflow.
Excellent. Well, thank you everybody for the feedback there. That's actually very helpful. So just to give a couple of examples of where we're considering going next, and obviously most of our future development is driven there by client feedback. So the first sort of stage of new functionality as well. Clearly at the moment we can test multiple scenarios and different ideas, but we want to make this as easy as possible. So integration with a Petrel workflow manager is key. So you can basically write a workflow and test different scenarios that you want to run. So if you want to see all 3 methods or 4 methods or whatever in comparison in terms of volume calculations, we can do that by running that through the Petrel workflow manager. It's interesting that we've had some suggestions for relative permeability curves. That's certainly on the list. I'll come to that in a moment. The first thing that we're currently working on is the integration with Techlog and or interacts with petrophysics. So we're starting with Techlog at the moment, basically because we have a very clever developer in house who has a lot of experience with Techlog. So the idea behind the Techlog integration is to not just make the transfer of logs between the 2 applications nice and simple and straightforward and seamless and easy to use, but also to bring across the saturation height functions that are made within Techlog. So Petrophysics obviously does a lot of very good work in putting those functions together, so we can bring those across into Petrel nice and easily, and then you can just run that function mapping workflow to then apply those height functions to the reservoir model. So what we're doing is creating that shared space, that common saturation model, so we get the geologists, reservoir engineers, petrophysicists talking, so there's one common saturation model across the discipline. So it's keeping that consistency between static and dynamic volumes, or trying to keep consistency, I should say, between static and dynamic volumes. So we're not going to spend as much time trying to investigate, why has one model got slightly less volume than the other and so forth. So we can try and just have one common saturation model. And then for the future, well, who knows? That's going to be driven largely by client feedback. We've had a few people obviously today and also spoken to me about relative permeability. So we can load capillary pressure data into AVA saturation, which then feeds through and stores that data in Petrel. So if we can load spreadsheet data which has got cap curves in it, there's no reason why we can't load RelPerm curves. It seems to make sense. And then all we need to do is, I'll say all we need to do, I don't need to do anything, it's the developers that do it. It's just then apply some formulas just to start generating relative permeability curves. So we've then got that consistency of the RelPerm curves and the cap curves together as well. So I think that's something that's very much on the roadmap as well. So I think that's all I have. So thank you very much, everybody, for your time and giving up your time from your busy days and for listening to me today. So just want to open the floor, shall we say, and just answer any questions that you may have.
Great. Thanks for presenting to us today, Matt. It's been really great to see how oversaturation can be used to calculate saturation height functions. As Matt said, we'll go ahead and take some questions now. And just a reminder that you can type your questions in the question box in your control panel, or instead you can use the raise your hand function if you wish to join the discussion verbally instead. Has anyone got any questions? So it seems we have a question from one of the attendees who wants to know, Matt, if the application is entirely cloud hosted.
Okay, so there's a cloud hosted part to the application, and it's also plugged into Petrel. So we run all the calculations from the cloud, but none of the data actually leaves Petrel. So the only bit of data that leaves Petrel is the UIDs, a long string of letters and numbers, which is the reference to the data object. So all the data basically remains secure and remains actually within the Petrel project that you're working in. So we don't take your log data to the cloud, but the calculations and the functionalities to say the FOIL function, that's based in the cloud, and that's where the instructions are sent from the cloud into the Petrel project.
Great, thanks, Matt. We also have a question regarding the audit trail. The question is whether it is written to the Petrel model or to the Ava web tool. For example, when we send a model to a partner, would they need just Petrel or the Ava saturation tool as well?
That's a good question. Yes, they will need both. But one of the things that we are working on, that we do realise, is that obviously reviewer licenses are obviously important. So because we need all the Petrel identifiers to run the calculations, it's very much linked with that particular Petrel project. But if you copy the project, you can send it on to somebody, and those references will remain within the saturation concept. But somebody will need saturation to be able to run or see your calculations. So what we can do in that situation is just to have a reviewer license available, whereby people can see what you've done, but not actually be able to go in and edit anything or rerun the calculations. So just be able to see step by step what has been done.
Great, thanks, Matt. We don't have time for a lot more questions, so if you do want to ask a question, I'd encourage you to type it out now. In the meantime, though, Matt, we have had a question about fluid contacts, and this attendee would like to know if we support fluid contacts as region properties.
Yes, good question. At the moment, I realise people have different ways of handling fluid contacts within Petrel. So a lot of people just will use either the segments or zone combinations, or other people use the region properties. At the moment, with the way that we're set up, we use the zone and segment combinations, because that's how we identify where the well sits within the grid. So that then feeds through into driving the calculations for height above free water level. So we're working on implementing the functionality to handle region-based properties, and that should be out very soon.
And continuing with the theme of fluid contacts, another of the webinar attendees wants to know if you see any value in including an excess pressure analysis to determine the fluid contacts.
Another good question. Well, what do I say? Yes and no, basically, is my answer to that. I think it's whilst including that analysis is very valuable. It's not strictly part of the sort of the niche technology that we're trying to address. So we're very much based on the assumption that you know where the free water level is, and that analysis has been done. But certainly, well, maybe that's another Ava technology that we can develop, which will then fit into Ava saturation.
It looks like we've covered all the questions. So Matt, is there anything else you'd like to cover before we wrap up?
No, I think that's absolutely everything from me. So just once again, thank you everybody for your time today and for listening to me for the last, oh goodness, hour or so. You can find us on the interweb. We've got the pds.group/oversaturation. We'll be at the AAPG in San Antonio in May. So if you go to the AAPG, please do come and find us and stop by. We have coffee in the morning. We have wine in the evening. And if anybody wants to have a chat, please do get in touch. If you've got any questions or you've got any feedback or you just want to know more, please do email me. My email address is there on the screen. It's matt.bowyer@pds.group. Thank you.
Thank you, everyone. We really appreciate you being here this afternoon, or if you're in other time zones, whatever time zone you're in. This webinar has been recorded and all attendees should receive a copy via email in the next 24 hours or so. Don't hold us to that deadline too strictly, but we will make it available to you. If you miss it on email, though, we will also make it available on our website, where you can also share the link with colleagues if you think they may be interested in it. As Matt said, if you wish to find out more about oversaturation, and if you think it can help you reduce uncertainty in your geomodels, please visit our website, www.pds.group/AVA-saturation. Stay tuned to our news and event pages on the website for details of other AVA webinars and events that we'll be holding throughout the year. We thank you again for joining us today, and we'll see you next time.